So good afternoon, everyone, and welcome to our third mechanical engineering webinar for today. My name is Megan Petrie, and I'm the Graduate Program Coordinator here in the Mechanical Engineering Department. And this afternoon, I am with Dr. McCluskey, who is the Division Leader for the Design and Systems Reliability Division, and he's going to talk a little bit today about their division and our department and hopefully answer all of your questions. And if you can't hear us or have any questions, feel free to put them up in the chat box. Go ahead.
Okay, welcome. I want to thank you for your interest in the Mechanical Engineering Department here at the University of Maryland, and in particular for taking a look at what we're doing in the Design and Systems Reliability Division. You may be wondering what exactly is covered by Design and Systems Reliability. So Design and Systems Reliability is the merger of three different research groups here on campus. The group that focuses on risk and reliability, there's a group that focuses on design and manufacturing, and there's a group that unites those two to look at design and manufacturing of electronic systems with an eye on risk management and improving the reliability of those systems. And the electronics that we do isn't particularly related to the electrical design, but rather to the mechanical design and how those systems can be made robust for harsh environment use, which we'll be talking about in much detail when we continue the presentation. So, as I mentioned, there's three groups. I'm going to go into each of the groups individually with a little bit more detail. The group that focuses on design and manufacturing has research in the areas of optimization, decision-making, product design, machine learning, and game theory. And what they like to do is they like to see how they can use those core technologies to improve the way people create, design, and manufacture all types of products that are currently being used in areas as diverse as robotics, healthcare, renewable energy, and experimental aircraft. In particular, a lot of work is going on how to make those systems autonomous, with autonomous robots and swarming, with autonomous cars for renewable energy, and autonomous drone aircraft. Now, the professors that are in that area, there we go. Professors that are in that area. Oh, oops, go back. There we go. Right. So the professors in that area do research. For example, in the upper right corner, you'll see examples of people who are working together designing complex systems. And so there's a lot of work in the psychology of how people work together, how they interact with machines, how they interact with software, and how the creative process works, so that they can design optimal teams that can design products in the shortest amount of time with the highest reliability, and do it efficiently and creatively. And so Professor Schmidt and Hermann have a number of different programs where they look at developing tools to help people work together to develop complex systems. Professor Fugue is working in our machine learning area, and so he looks at how can computers be used in the design process to improve creativity, to evaluate different types of the design space that maybe people have traditionally not looked at because they've been sort of constrained by their own preconceived notions of what certain products are supposed to look like. And he also takes a look at how you can use those computers that you use for design, how you can use those to work in 3D printing to manufacture their own design. So can you manufacture your own, in this case, soft robots, which he has shown in those beakers there. And there's a video that we can use. There's a video that we can use there's a video that we can use to show how that works. We also have Professor Herman and Professor Azarm who look at optimization and how does one use optimization theory to design and control autonomous systems. How do you handle all the different pieces of information that are coming in from different locations, and how is that information collected and used. We have Professors Gabriel and Azarm that look at how do we design systems to meet certain market forces of time to market, cost to market. And then finally, an example of a rather forward-looking piece of work that's being done in this area. Just one typical example is the creation of 3D printable heart grafts for children, which is being done by Professor Fugue and Krieger. Other examples are using different types of systems to look at epidemiology or to look at sales. So there's lots of ways in which these advanced design tools are being used to improve the manufacturing process. Okay, if we go to the next slide, we'll go to the second group. The second group is risk and reliability group, and their focus is on not necessarily removing all failures, but understanding how failures occur, what the basic physics is behind those failures, looking at how one can use a combination of modeling and accelerated testing to predict those failures, and how one can then take that information and use it to manage risk and to make decisions in design to minimize or optimize the risk level that you're willing to take across multiple different situations. One area in particular where they're looking these days is how to incorporate machine learning into understanding how systems fail by collecting information during the life of the product and then determining what the expected additional life will be based on, or what possible failures may occur based on what's happened in the past. And we'll talk a little bit more in detail about that also as we go along. And of course, one big application for this type of work right now is in cybersecurity, and looking at what are the possible ways that software systems can fail or be attacked or be hacked, and what kind of effects certain software attacks would have on the reliability of the product or the system or the network as a whole. So there's a lot of work in that cybersecurity area. But it's not the only area they're looking at. They also look at critical infrastructure like bridges and airplanes. They look at autonomous systems like drones and swarming vehicles, and they look at healthcare as well. And examples of the work that's going on there include how should we design our critical infrastructure for improved risk and reliability. And so examples would be next generation facilities such as hydrogen storage facilities, but also nuclear facilities, also bridges and aircraft, etc. Another thing is how do we enable safe human-machine or human-system interaction? As more and more autonomous and driver-assist controls are placed in cars and planes, the interaction between the driver and those automatic control systems, and when to use the automatic control and when to rely on the driver, and how they interact with each other, and how the information that's coming into the car is processed, that all becomes critically important, and understanding how to manage all those different incoming data streams. And then finally, how do you quantify these system risks to cybersecurity? The professors who lead in this area are Professors Katrine Groth, Mohammed Madaris, Manifa Von Cook, and also Michel Cuquier. And Our third area is our electronic systems group. And I hope I see the whole screen here. Okay. With our electronic systems group, you'll see there's a little overlap with the other two areas, because what's happening there is you're taking the technologies from both risk and reliability and design and manufacturing and focusing on a specific type of application. And that application is robustly designed electronic systems where there's a reduced risk of mechanical failure. And areas where electronic systems are particularly susceptible to mechanical failures are things like aviation, where you're dealing with lower pressures and high G-forces during launch, and cold and hot temperatures, healthcare, renewable energy areas where, for example, there's a lot of power electronics to distribute the renewable energy. Those can get very hot. And we also apply this to additive manufacturing. So the areas that we look at for electronic systems are reliability, science, prognostics and diagnostics, which is understanding what the characteristics of failure look like, and then using that information to predict how long systems will last. What are the impacts of reliability on the cost of the overall product, along with, as mentioned before, risk and reliability, the development of models and testing procedures to improve that reliability. So examples of that type of work, okay, include the development of new optical devices, new semiconductor devices, and new semiconductor devices that can operate over wider temperature ranges. And that's work that's being pursued by Professor Han and Christou. In addition to your switching devices, which are your optics and your semiconductors, we also need energy storage. So there's a lot of work on how batteries perform and how we can predict and diagnose failures that limit battery life, and how can we extend battery life. That's work being done by Professor Peck. A lot of systems are maintained for a great deal of time. For example, recently people have looked at taking the B-52 bomber, which was first released in 1948, and seeing if we can continue to manufacture that to 2048. So certainly there's been a lot of advances in electronics between 1948 and 2048. So how many spares do we need of the old technology? When should we have a design refresh with the new technology? When do you maintain? How do you maintain? And when do you upgrade such legacy systems? And Professor Sanborn leads in that area. I take a look at designing electronics for extreme harsh environments. I also work with Professors Dasgupta, Das, and Ohadi at Additive Manufacturing Electronics, and at looking at thermal management for electronics, particularly in the area of power electronics and motor design, also again with Professor Ohadi, but this time as well with Professor Mark Cohen. And if you look at the pictures on the right-hand side, the top is the power module. In the middle, you see some printed electronics that are both placed on a prosthetic arm, or could also be placed as a sensor system on an actual arm for health monitoring. You see some coils that have been 3D printed and 3D printing on a dome. You also see the packaging that goes into making an Apple iPhone, and finally at the bottom you see power electronics integrated onto a high-power motor. So we'll take a little, this is the area which I do a lot of my research, we'll take a look a little bit deeper into how this works. One of the things we find is that electronics used to be confined to large computers sitting in air-conditioned rooms. But that's not true anymore. Now all the electronics are at best on the cell phone sitting in your pocket, where they're susceptible to being dropped on the floor. They may encounter moisture if it's a rainy day. They may see differences in humidity, differences in temperature. So they need to see a particularly diverse set of environments. And that's just the simple consumer electronics that you have available to you. When you start to talk about systems that are being used for high power, for example, in the smart grid or in aircraft or on ships, all of a sudden you're talking about a completely different set of harsh environments. You may be exposed to very high temperatures, for example, over 200 degrees C when you're on a mission to another planet. You may see very cold temperatures below 200 degrees C. You may see very high pressures up to 20,000 psi when you're underground looking for geothermal energy or for oil. You may see large amounts of shock and vibration, for example, driving over a cobblestone street. You may see road salt if you're driving. You may see sea spray if you're on a boat. So there's all types of different environments that can wreak havoc on an electronic system. And it's not getting any better. If you look at current power electronic systems, we're tending to pack more and more power into a smaller and smaller volume, and that means the power densities and therefore the heat that's generated by those electronics is increasing all the time. And in addition to this higher heat, that means we have to incorporate thermal management systems into the electronics to cool them down, okay? And it's not just internal heat that's being generated, but as I mentioned, you also are placing these in some pretty severe environments, ranging all the way from space to the Arctic and Antarctic. So, and when we talk about ensuring stability over these wide temperature ranges, we're not just talking about temperature, as I mentioned. We're also talking about a series of other things, and I've mentioned them here as well. Mechanical reliability has to do with everything from pressure to shock to salt to corrosion to, in the case of power electronics, high voltage and high current. So what do we do? Well, if you look at an electronic system, it's got the chip, which does the actual brains of the system. But there's also the packaging that's around the chip, and that's everything that gets the signal from the microprocessor that's doing the calculation all the way out to the human being and all the way back again. So everything from the keyboard to the wires to the housing to the printed wiring boards to the solder joints to the components and so on. And so we work at all those different levels. And for example, one area, if you just start really close to the die, you can start with copper or wire bonds. Traditionally, people have wire bonded with gold for high reliability. Gold became very expensive, so people wanted to see if maybe they could wire bond with copper. After all, you have copper wire in your house. Why couldn't you have copper wire in your electronic components? Well, while they're cheaper, there are a lot of issues involved in making those bonds strong and reliable. And so we are doing a great deal of research to take a look at what are the failure mechanisms that can occur in these new wires. And one of the things that happens is that they fail in many, copper wire bonds fail in many different ways that are completely different from the way gold wire bonds used to fail. So with gold wires, when you pushed on them, they would fail through the gold. With copper wire bonds, when you push on them, they fail through the aluminum pad that's under the wire. So they don't fail in the copper like they failed in the gold. They fail in the underlying pad. Another thing that happens is you get intermetallic formation where the copper and aluminum react, and that is also affected by the type of bonding process that you do. So we're developing new standards to make sure that they're reliable. One of the things we find is that people don't like wires because they're tend to be a large tangled group, and you have to have very, very thin wires in order to make all the inputs and outputs. So it'd be really nice if you could get rid of them and just connect everything with little solder balls. And so there's a move from wire bonding to centered interconnect, where people are trying to get rid of all the wires that are present in an electronic module and replace them with just solder joints. That's great because it eliminates wire bond failure, and it also lets you cool the package a little bit easier. But it means that you need to really worry about your wires. You need to worry about your solder. So we have programs where we're actually looking at new solder technology. So one of the things we've done is we've taken a look at materials that basically are very similar to the metals that used to be used for dental fittings and cavities. And what we do is we take two metals, one that's high temperature and one that's low temperature. We melt the low temperature one and allow the still solid high temperature metal to react with the liquid low temperature metal to create a compound that then solidifies and has a melting point that is somewhere in between the higher and the lower melting point of the two constituents that it's made of. This allows us to do soldering at very low temperatures where the lower material melts, but then have that solder joint be very reliable up to much higher temperatures where we would want to operate the electronics. So we can do it at low temperature, not damage the electronics, but then have it able to be operated at a much higher temperature. And so these types of material systems, which we have developed, are now being considered for use in a wide variety of different applications, ranging from high temperature capacitors to high temperature attachment for switches to even 3D printing. Some of the research we've done on this is developing the process for creating the joints, showing that they retain high strength up to extremely high temperatures of over 600 degrees C, looking at how the phases grow and how the reliability changes over time, and then characterizing how well they do in temperature cycling and power cycling, where these solder materials could undergo fatigue due to the stresses that are imposed when you either cycle them thermally or you expose them to shock and vibration. You have to attach down to something, so if you're attaching your chip down with a solder to a base plate, it's important to understand what's going on in the base plate. Traditionally, these substrates have been made of a very thick copper that's deposited on a ceramic. When you cycle those at wide temperature ranges, the copper tends to peel off the ceramic. So we've looked at all different types of ways to improve that process, either by reducing the stress in the copper, by putting the copper under residual compressive stress, thinning the copper at the edges so there was less stress, or strengthening the ceramic. And we've even gone to the point of developing new materials where we use aluminum instead of copper, because the aluminum will actually yield and flow at a lower temperature than the copper, thereby just having the material adjust, the aluminum will adjust to the expansion of the ceramic rather than peel off or crack the ceramic due to stress. So we've looked at different types of approaches to that as well. And having looked at the substrate materials, the wire bond interconnects, and the die attach, we then, of course, wanted to know, could we possibly additively manufacture all of these components and make entire electronic circuits by doing 3D printing rather than using more traditional approaches that people have used in the past. So currently, together with some of the other professors in the department, we are looking at, first, can we 2D print some of these materials on curved surfaces? So can we print the same lines, and can we print the same wires that you would print on a printed wiring board, a flat printed wiring board? Could you possibly print those by 3D printing on a dome to make an antenna? Or could you print them on a flexible piece of material that you might wear as clothing? Or could you print them onto a curved surface like the wing of an airplane? And so the first thing is to see if we could print the circuits on 3D materials. Then the next thing was, could we make 3D structures with 3D printing? So could we not only print the circuits, could we also print the pins? Could we print the connectors? Could we print some of the components? So we're actually looking at all those different areas of additively manufacturing electronics, both on this slide, which talks specifically about using metal nanoparticle inks to print traces on 3D parts, but also in the next one you'll see, or actually in the next one after that, you'll see that it's actually possible in the lower left-hand corner to create 3D printed components like inductors, resistors, and capacitors, to 3D print layers for, in this case in the middle, a barium titanate capacitor, and even 3D print metals to create thermal management systems such as the air-cooled heat sink there that are of complex airflow patterns that could not be made by standard manufacturing procedures. So some of the things that we're looking at. Go back here. Okay. So some of the things that we're looking at are we're looking at wearable electronics, as I mentioned. We're looking at being able to print electronics wherever you are. So you would have to source spares, for example, for maintaining systems. Something broke, you could print the part right there. We're looking at doing it for difficult geometries where traditional printing techniques are very difficult to use. And opportunities are in everything from the military to telecom to automotive to energy. And as I mentioned before, on the left, upper left there, you see actual electronics that are tattooed onto a person in order to measure, for example, sweating of the skin, temperature of the skin, heartbeat, etc., for health monitoring. You can also see there printing for the soldier of the future in the bottom there as well. And then, as I mentioned, since our focus is risk and reliability as well as design and manufacture, we want to be looking at what can go wrong with these additively manufactured systems. And they're very different processing than the traditional processing. So we kind of know how a cast material will fail. We kind of know how a rolled piece of metal will fail. But we don't really know how some of these additively manufactured metals and ceramics will fail because nobody's manufactured that way before, and they have lots of interesting characteristics. For example, when you cast a metal, you cast an entire bulk material, or when you roll or draw a material like a wire or a piece of sheet metal, you've got a bulk piece of material. So with these additively manufactured systems, they tend to be made in layers. So you'll lay a layer of material down. The next layer goes down after that. Well, that makes an artificial interface between the first and second layer. So now these things are being stacked up like layer cakes as opposed to being made as one uniform, homogeneous bulk material. And so you have to worry about how well those layers are going to stick together, how well they're going to meld together, whether there are going to be changes in their properties in the Z direction where the layers have all the boundaries. Those are some things to look at. Also, these materials tend to be a lot more porous because they tend to be made by fusing particles together. And so as a result, you have a lot more gaps and a lot more pores that could initiate cracks. It's another area. They tend to have a very high surface to volume ratio because you're making very complex structures that you can't make otherwise. So you have a lot of surface interactions. Films can form, reactions can occur. You also have the possibility of having artificial microstructures. So perhaps your material is stretched out because you're doing it as a line when you print it, okay? Whereas if you were to pour it out, it would be more circular or more equal in properties in all directions. If you do it in one long line, you may stretch the boundaries out in that line. So a lot of differences in the way that the system works. Also, you got a lot of residual stresses because as you lay down each layer and solidify it, when you put the next layer down, that's going to generate stress in the layer underneath. So there's a lot of things that have happened, and since there's so many different ways to make additive manufactured products, these are all process dependent as well. So we study a lot of the areas involved in the reliability there as well. Having made it, generating a lot of heat, maybe you have to put some thermal management in there, so we look at a lot of thermal management tools that can be used to remove heat from high-powered electronics, where a lot of heat is being generated. The first thing you can do is just stack those electronics up on a lot of layers that can absorb and dissipate heat. So you want a lot of materials that both have a high specific heat so they can grab heat from the device, okay, and then a lot of thermal conductivity so it can shed it out, okay. In some applications, it's more important that they store the heat, so that you want to pull the heat out of the chip and have it stored in a material that has a high specific heat. In other cases, it's more important to get rid of it right away, in which case you want to pull it out and use the thermal conductivity to dissipate the heat. So the first step is to stack these materials on different thermal interface materials that can spread and store or remove the heat. The next thing is, what are you going to remove the heat to? Well, typically you either have to flow air by something or you have to flow liquid by something so that the airflow or the liquid flow can pick that heat up and transport it out of there. So we look a lot at how do we do convective heat transfer through air and liquid-cooled heat sinks. And then, of course, one of the most efficient ways to get rid of heat is to use the fact that as you melt something or boil something, it absorbs a lot of heat to that process. So changing from solid to liquid is called a phase change material, and we'll do that to store heat that we may want later on down the line. So we may, if there's a very, very rapid spike in temperature, we may pull that heat out, causing a solid to liquefy, and then later on, when the chip is off, we may allow that heat to slowly dissipate away, re-solidifying the material. That's phase change. We also may do it with liquid to gas. So we may take a liquid, flow it over a surface, let it boil away into a gas, then take it out to an area where it condenses and comes back as a liquid again. And that's kind of what the radiator in your car does. When it basically takes cold fluid, flows it over the engine, takes that heat away, then goes into the radiator, where then the airflow allows that liquid to shed the heat to the air. So we do a lot of heat exchanger type work, but on a very, very small scale. We're talking micron and nano-sized structures to be integrated directly in with the electronic package to remove that heat. And then we may combine different things. So we may use heat spreading in one place combined with thermoelectric cooling in another, or we might use two-phase cooling in one area and just single-phase liquid cooling in another. So we may combine these to allow us to address certain hotspot areas with a highly complex and costly technique that may not be needed for the rest of the system. So we'll combine them together. And one place where we're starting to use a number of these techniques are in smart motors. So motors typically were just electromechanical systems, and all their control electronics were located separately from them in a motor drive. And so there'd be these wires between this box that drove the motor and the actual motor. Well, people don't want to do that anymore. They want to integrate all that control directly on the motor. So they want to put the switching devices and the control devices right there on the motor so that they can have one integrated motor system that has its own drive electronics associated with it. Okay. In addition, they want the motors to be higher and higher and higher power. So one area where this is particularly important is in the area of autonomous flight vehicles. Vehicles where you may want to be able to transport 4, 6, 8 people, okay, in an autonomous air taxi. It's going to require motors that are megawatt in size in order to do this. And so that means even if the motor is 90% efficient, you've got 100 kilowatts of heat that you have to get rid of. So we're looking at new techniques and new technologies to improve the way in which we remove heat from motors. Then if the control electronics are also integrated into the motor, then you have to get the heat out of the electronics as well. And in many cases, the electronics have to be held to a lower temperature than the motor can run at. So you're talking about getting all the motor heat out and also all the electrical heat out, and also not having the hot motor affect the performance of the electronics. So there's a lot of thermal management in cooling the motor, cooling the electronics, and making sure that they're isolated from one another thermally while they're packed very tightly together mechanically. And we're actually looking at doing this for a 737 size aircraft in which you would use 8 2.5 megawatt motors together to provide all the thrust necessary to lift 137 people up into the air. So we're talking about a fairly large size plane, all done with electric power, all done with electric motors, and the idea there being that we need to provide the same kind of levels of thrust with electric motors that we're now able to do with jet engines. So there's a lot of interest in electric propulsion, all the way from air taxis to large-scale aircraft, and all the thermal and reliability aspects that come to bear in doing such a system. Okay, great. The last thing I want to talk about before we break is our work in what we call prognostics and health management. In addition to looking at how do we design systems for harsh environment and how do we manufacture them through additive manufacturing, how do we cool them through various thermal management, we also want to look at assessing their life and determining what types of failure mechanisms may occur and how long the parts can last. Traditionally, this was done from a very fundamental standpoint where we would look at all the different ways in which the system could fail, model those, and then take a look at the environment it was going to be in and predict how long it would take, for example, for corrosion to occur or for fatigue to occur. That's still the basis of the modeling that we're doing, but we're now adding a little bit of machine learning to that. We're actually going out and collecting data on the part as it is actually used in service. This tells us not only the environment it's in, but we can monitor indicators of how the system is performing. And if we start to see the system lose in performance, that will give us a clue that degradation is occurring. And by the amount that the performance goes down, we can determine how much longer that part may last before it's going to fail. An example of this, a simple example of this is in fans. If a fan is running and it's making a nice, it's running very smoothly and makes very little noise, you know the fan is in good shape. When the fan starts to shake and rattle and make a lot of noise, well, you know that the bearings are starting to go bad, and pretty soon the fan's going to die. So that's a simple example of what we're doing. We tend to do it not with fans, but with electronics, and we actually watch the electrical signals. And as we see the electrical signals change, that gives us an indication that maybe the mechanical system, the mechanical aspects of the device are starting to degrade. Chips are coming loose, wire bonds are breaking, those types of things. Okay, so we combine our basic understanding of physics of failure, which we call life consumption monitoring, with our data analysis that we do in condition monitoring, and we put it together to get the remaining useful life. We've done this not only with, we've done this with all kinds of systems, but in particular we're looking again at power electronics. In my group, we monitor the signals that can be related to the operating system. We detect when they're deviating from normal operation. We figure out why they're deviating from normal operation based on when we've seen these types of deviations before and what they've signified. Then we go to our models and predict if they've failed a certain amount so far, if there's so much degradation we see so far, how long will they last? And then you can change the operation. Maybe you run them a little bit less often, maybe a little bit less load, okay? And therefore optimize the length of time that the product can last. Here's an example of a power module. We've looked at the voltages and currents that come out of the power module, and we've used that to diagnose when we think the power module is going to fail. In addition, we've used machine learning technologies for looking at new parts. We're able to look at a wide range of different characteristics, 20, 30 different characteristics in a number of different components. And we see which sets of characteristics lead to long life and which sets of characteristics lead to short life. And we don't have to separate the characteristics out. We don't have to know individually what each effect has. We just know that parts with long life have this set of characteristics. Parts with short life have this other set of characteristics. Then we can look at a new part, one we've done no testing on and no modeling, and we can just see whether its characteristics are more like the long life one or the short life one, and thereby predict how long the new part will last. And that's a way of using machine learning technologies to be able to look at very complex systems where you can't look at each individual factor and figure out whether it's going to be a long life system or a short life system. And so we have research going into how that process can occur. And lastly, this type of health management using machine learning and physics-based modeling is now being used for everything from batteries to circuits to wind turbines to helicopters to everything. And it consists of basically designing it, learning about it, monitoring it, processing that information, diagnosing what's wrong, figuring out how long it's going to last, and then putting that information back to work again. So if you're interested in learning more about these different areas, we have a number of professors in the Design and Systems Reliability Division that can help you out. Dr. Azarn is our leader for design optimization, Dr. Barcohen for heat transfer, Dr. Biggio focuses on quality, while Dr. Christou focuses on electronic devices. Professor Kukier is our cybersecurity person, and Professor Dasgupta is involved in electronic materials characterization. Professor Fugue is our expert on machine learning. Professor Gabriel looks at game theory and reliability assessment. Professor Groth is involved in understanding the reliability of systems for critical infrastructure. Professor Hahn looks at metrology and how do we measure characteristics of electronics. Professor Herman's in our design reliability group, while I do the extreme environment and mechanical design of electronics. And finally, we have Professor Modaris, who specializes in reliability theory, Professor Peck, who's involved in prognostics and battery reliability, Dr. Sanborn does our cost analysis and our long-term sustainment systems, Linda Schmidt's looking a lot at how people design and how creativity can be optimized in large group design settings. And finally, Professor Von Cook is involved in human factors and human-machine interaction. So with that, I'll conclude the presentation and ask if there are any questions so I can tell you a little bit more about what we do in design and systems reliability. So thanks for your attention, and look forward to hearing more from you during the question session. So thank you.
Thank you. So if there are any questions, feel free to put them in our chat box. And you can also email the graduate program at megrad@umd.edu, and we can forward your questions on to any of the faculty or answer them if they're about admission. So feel free to put your questions in the chat box. One last question as we wrap up. Is there anything that you think that really sets Maryland apart from other mechanical engineering programs?
Oh, good question. I think that we have we have a lot of good resources. We have experts in, I would say, very, very strong experts in the field of thermal management, risk and reliability. Our electronic products and systems group and its focus on risk and reliability is completely unique. We're the go-to place for anything related to reliability of electronics and electronic packaging. We don't necessarily the go-to place for circuit design, and we're not necessarily the go-to place for the cheapest packaging, but when it comes to harsh environment, high reliability, risk management of electronics and electronic packaging, that's really a big, strong focus of our group. I'll also say that we have a nice balance between the practical and the theoretical, which allows us to really excel versus other universities.
Mm-hmm. And is there any advice that you would give to students as they're applying and looking to talk to faculty members during that process?
I would suggest that you take a look at what the different faculty members are involved in on their websites and through their journal articles. Find ones that match your interest area, and then make contact, direct contact through email or a phone call with that, or through their website with that faculty member. So you get a chance to learn a little bit more about what they do and what openings are available before you apply. That'll give you a better sense of what you're going to actually encounter when you get here.
Mm-hmm. And if they don't hear from you right away, is it okay after a couple of weeks to ping you again?
Yes. We're all very busy. A lot of us are traveling overseas, so a lot of times we will miss things. So yes, definitely don't mind several pings.
And I guess one last question, since I still don't see anything from anybody else. Is there any innovation or anything exciting coming up that you're really excited about within the DRS world?
I guess the biggest thing that's going on right now is that if you had asked me maybe 2 or 3 years ago, I would have said the additive manufacturing, because there's a lot of opportunities for us to make new structures in electronics that we haven't made before, and to manufacture parts we haven't been able to manufacture before, and study their reliability. And today, that would be 2 or 3 years ago, today I would say that that's now maturing, and we're still doing a lot of research in that area. Now I would say it's the machine learning. I would say it's how we're applying machine learning to design, to creativity, to manufacturing, to collecting data on our products and understanding their reliability, their risk, using it to improve systems. So I think this learning about how machine learning and data is involved in the systems is kind of our big area right now. And it's going to just like additive manufacturing, the two together are going to allow us to create products we haven't even dreamed of before, which is what I think is really exciting.
Mm-hmm. So there's a lot to come.
Hey, very much so. And hopefully you'll come here and be part of it.
Exactly. Like I said, if you have any questions, feel free to reach out to the graduate program or Dr. McCluskey. So thank you so much for your time.
Thank you.